Thank you. And I'm really excited to be here today. Can you hear me okay over there? Yes? Yes? Okay. So it's always fun to talk to this group, but I think the presentation for tonight is an interesting presentation. The job for me today was to give you a nice, comprehensive overview of the highlights of our knowledge of brain discoveries, giving you the more interesting and amazing discoveries of the brain. And that's what I'm going to try to do over the course of the next 1.5 hours. It's a big talk. It's very comprehensive. I'm going to try to keep it as simple as I can. The first few slides are going to be some of the denser and tougher ones, and after that, we're just going to be rolling. So think about it as a roller coaster. We're going to have the first tough ones at the beginning, so keep your focus and concentration. And then we're going to slide down, and we have some deep scientific information, and then some relaxing and interesting information to go along with that. So hopefully, at the end of the afternoon, you'll have a far better understanding of the brain, its function, how is it made, how does it work, what is it important, the different parts of the brain. And I understand I'm not going to be able to cover everything on the brain. I just tried to pick up the things that I thought were most important. And you don't have to learn everything. There's going to be a lot of information that we're going to be covering. It's going to be a dense topic. But if you get tired, if you take a little nap, if you need to go to the bathroom, if your telephone rings, it's fine. It doesn't bother me. You know, you're not going to lose the ideas and the concepts that you need to learn. I have made a small handout of some definitions, some of them pretty simple, but just to give you an idea of some of the concepts that I'm going to be talking about today. Our conference is going to be recorded. Now, if you have a particular question about something that I said that for some reason, like my accent, you didn't understand, just ask me and I repeat it. If you have a burning question about something that you always wanted to know, just write it down, and at the end, we'll have enough time for questions and answers. I have a whole hour and a half, and trust me, I cannot talk for that long. It's going to be tough for you and for me. Think about this talk as a free guided tour to the Brain Museum. And that's basically what we're going to do. We're going to put some slides out that cover some of the most interesting and important highlights of the discoveries of the brain, the people that made the discoveries, how were they made, what relevance they have to our knowledge of brain tissue. And if you have any questions, if there's something that you really wanted to know about the brain that we didn't cover, we'll have time to talk about it at the end. This is a good time for you to write down on your pieces of paper any questions that you have, and we'll go over at the end. We'll hopefully have enough time for questions and answers. So where do we came from? Where did the brain came from? How is our brain made? How is it composed? How does it function? I mean, it's a great question. It's one of the biggest questions that humanity have asked itself. And I think you have to go back to the formation of the brain. And if you look at the evolutionary advances on the brain, the fish came out of water about 360 million years ago. The mammals came about 200 million years ago. And then the apes family came about 80 million years ago. That's our biggest family. From there, we have some human precursors that were around about 4 million. These are million years ago. And we started to change until about the last 100 to 200,000 years was when modern humans came to Earth or appeared on Earth. So we are the ones in the middle, the Homo sapiens. We came from a big family. And, you know, some people look at these pictures, and to them it seems like a cartoon picture. But actually, when you look at the human skulls available through the World Museum, we have more than 5,000 skulls that give us the history of transition on the human brain with time. The changes came slowly and gradually, and there were many factors that lead to them. One of the important ones happened close to this time, about 2.4 million years ago, when our ancestors' skull looked somewhat like this. It was a very narrow brain, because it had to allow a lot of space for the temporal bones, for the temporal muscle to be able to connect and have some space for the chewing effort. The apes have strong chewing. If you've ever been bitten by an ape, okay, you realize how hard their jaw is. Well, about 2.4 million years ago, there was a mutation that affected one of the main muscles on the temporal lobe of those apes. What happened is that it made that muscle weaker. So that muscle becoming weaker, it allowed for the brain, the sutures, the soft spots in the brain, to grow a little bit bigger on our development and allow the brain to grow. And, you know, mutations, we think of mutations as something that happen rarely, and it's something abnormal, but mutations happen hundreds of times in every cell in our body. So mutations are very common. Most of mutations that we have, they don't cause a lot of problems. They stay in the cells. They don't cause a lot of damage. Some are beneficial. Some cause some damage. But some of them are very critical, and this seems to be one of many. Just to give you one example of many mutations that lead through lifespan in humanity that was critical information of the brain. It's amazing to think that from one cell, everything was formed. And I think a good example of that is the brain. So you have the little sperm that came and it got into the egg, and the egg formed the first cell on the humans, and that cell started to develop in the embryo, and it formed 4 and 8 and 16 and 32 and 64 and hundreds of cells, all identical. And then at one magical point in embryological development, those cells in the human, they started to change. And those cells that were initially identical suddenly start producing cells that will lead to hair tissue and skin tissue and teeth and heart and lungs and all of the body organs, and obviously to the brain. And the brain, of all the tissues in the body, is really obviously the most important part of the body and the one that controls everything. So when you look at the embryological development, you look at the first few weeks of conception, we have more or less a brain taking its shape. At those initial months of growth of the brain in the embryo, we're producing 250,000 cells every minute. So the cells are dividing that fast, and they're developing and evolving, producing different type of brain cells to form all of the cells that constitute the brain tissue. By the time in gestation that we're 8 months, just before we're born, we have about twice the number of cells that humans will have as an adult. So the brain produces initially far more cells than we need, and then at birth and after birth, those cells that don't make good connections, that their function was mainly scaffolding, helping others get to the place that they needed to be, the ones that didn't develop well, we start destroying them by a normal process called pruning, and then we get to the normal human brain. It's very hard to understand brain function. Trust me, I've been trying for the last 30 years to try to figure it out and still having trouble with it. But a very simple way to look at it that will give us a good overall idea of how the brain works, it's summarized in this picture. So that's an important picture to have some basic concepts. So when you look at the brain of fish, the fish basically have a cerebellum. The back of the brain, the cerebellum, controls the coordination. So what do fish do? They're in the water, they move around, they eat. And then the reptiles start having a little bit more brain function. They have, you know, for what us is our brainstem, is considered the reptilian brain, whose main function, not all of the functions, but the main functions have to do with feeding, fighting, fleeing, and reproduction. So when you think of the reptilian brain or brainstem function, those are some of the basic functions of life. That's what keeps life going. If you look at lizards, for example, I enjoy watching them in my yard. They run, they attack, they eat, they have sex, they mate. It's so funny how you see them when they kind of trap each other all over. They eat, they flee. If they're scared, they run. If they can attack, they attack. So those are the basic functions of life. That's what keeps us alive. Our instinct to eat, to reproduce, to fight, or to flight. And that's a reptilian brain. So as the brain develops, then the limbic system develops. So the limbic system is the part of the brain that have to do with emotions. Emotions and memory. Think of that as the more important part of the limbic system. All mammals have a limbic system. So that's why you can see a dog, a cat, any mammal, they can look at another animal down the road and they can figure out, is that tiger is going to eat me or is it going to be friendly? So then based on emotions, on smile, on movement, they can figure out, well, I don't think that lion like me. I think I better run away from it. So the emotions are developed within the limbic system. They're critical for survival. They're critical in controlling our basic reptilian or brainstem function. And then mammals, and particularly humans, but most mammals develop what's called a neocortex. So the neocortex is the brain itself. When we think of the brain tissue, when we think of the things that the brain do, the thinking, the language, the processing of information, their analysis, how do we think of other people and each other, all of the cognitive function is done in the brain. So how the brain function in a way have to do with the connection between this system. Are you somebody that are more of a reactive person, spontaneous, you work on your instincts, or are you somebody that is going to be more rational in your approach? So how those systems work together is one of the bases of what makes the brain function well. When you think of the brain, people think of the heart and the liver as organs, but the brain is just not a simple organ. I mean, I have talked to you before that I always made that same point. When you look at the brain does the locomotion, the movement function, understanding, comprehension, speech, vision recognition. There's many functions that the brain do, and it's just unfair for people that categorize the brain as a simple organ because it is not based on its function. The adult brain weighs about 3 pounds, so it's really not that heavy. It's only about 2% of the adult weight, but it receives about 20% of the cardiac output. So of the blood that the heart is pushing out, 20% goes to the brain. Okay? So the heart is meant to maintain the brain, in a sense of the word. It's composed of water, fat, and protein mainly. It has, and we don't know for sure the numbers, because nobody has really sitting down and count billions of neurons in a brain, but it's been estimated that we have about 2 to 10 billion neurons. Again, as you know, the neurons are the main brain cells, the cells that do most of the function that we think of when we think of brain function. But then we have another very important brain cells called the glial cells. The glial cells is the support system of the brain. It's a number of different group of cells that do the cleaning, the maintenance, the protection of the neurons. So we have the neurons as the main cells, and we have the glial cells, and those are about 10 times more common as the neurons. Those cells don't touch each other. Okay? As tight as the brain may look for that number of cells, the cells don't touch each other. They communicate to a little gap between the cells called the synapses. And that's not on your definition, but if you haven't heard that word or know about it, write it down. So the synapses is the little gap or space between cells where the communication between one cell and the other take place. There are about 100 naturally occurring neurotransmitters. When I first prepared this slide a few years ago, I had 70 there. Every time I review this lecture, I have to start increasing the numbers. And there are more to be discovered. And every single neuron connects with so many other neurons that we have 100 trillion synapses. The synapses are the connections between one nerve cell and another. Okay? So you don't have to know this data. You have to understand that the brain is far more complex than we can imagine. And then we don't know how many genes exactly are active in the brain. We know that in embryological development, 80 to 90% of the genes that we have in our chromosomes are active in the brain, and in an adult, about 33 to 66% of our genes are meant to be active in the brain. Of the genes that we have active, because remember, we have a lot of genes that we don't use. For example, the gene for a tail is a gene that we have, it doesn't work. The gene to produce vitamin C, we have a deficient gene to produce vitamin C, is not working. So we have a lot of genes that don't have an use in us, it's being disabled, damaged, or we don't know how they work. But let's go back a little bit to the beginning of our understanding of brain function. I mean, for a minute you think that you know nothing about the brain, which is probably right. And we want to start from scratch now. We're going to take you back to the beginning. So humans came to Earth, they started spreading through the world, at about 10,000 years ago, civilization started. That was when the time where humans start forming groups and settling in places. So once the humans start to settle, they start developing communities and farming and taking care of animals. And then they were able to develop more complex language and writing. The more interesting and complex civilizations were the Egyptian civilizations. And I want to mention them because the first time ever that is being documented that humans took a look at a brain were the Egyptians. So when the Egyptians were preparing the dead body for the afterlife, what they did is that they would prepare the body and they would put a little nail through their nose and drain the brain tissue and get rid of it. So they felt that something that was sticky, gelatinous, watery, breakable, smelly, couldn't have any decent function. So they would get rid of the brain and prepare the rest of the body. So following that, through the Middle Ages, there was not a lot of work done on the brain and how the brain functioned. Nobody really tackled that issue. And then hundreds of years later, in the Renaissance, in the late 1400s, 1500s, it was the first time when the church opened in Europe the capability for people to do autopsies and look at the body. And one of the most important things that the Renaissance gave humanity was the increase in anatomical knowledge. That was the first time that we were finally opening bodies in detail, looking at them, looking at the connections in the body, looking at how things work, evaluating the circulation, the blood flow, the lung function, the kidneys, and everything. That started with the Renaissance. So we're talking in the 1500s, but it was not until the 1600s, in the famous Oxford University in England, that a group of people decided, a group of great scientists decided, we're going to see what's going on in the brain. We're going to figure out how the brain works. We're going to start doing some studies on how the brain works. At that time, there was no preservation methods, so people couldn't hold a brain and look at it for any period of time. So Thomas Willis, which is the one pictured here, and his group of physicians and scientists from Oxford University started doing studies on the brain. They were the first one that developed brain preservation techniques. They developed dissection techniques, so they were able to get the brain out just before them. Leeuwenhoek invented the microscope, so they were able to take slices of the brain, look at them under the microscope. With preservation, they were able to cut a brain in different areas, look at it, and try to recognize the different parts of the brain, follow the spinal cord, and see how the spinal cord connects through the brainstem into the brain. So these people were the first one that did this study. This is a picture. The first time ever that humans look at a brain through a picture was through that picture. Christopher Wren, that most of you know as the man that reconstructed London after the big fire of London and constructed the St. Paul Church Cathedral in London, he was working with Thomas Willis, and he was the one doing the drawings for them. He was the one that did the first painting of the brain that was published on his book, and still anatomically perfect, showing the frontal lobe, the temporal lobe, the cerebellum, the brainstem, the chiasm, the optic nerve, the olfactory nerve, and other structures that we don't have to learn in detail. So Thomas Willis and his group They developed the brain preservation techniques. They were the first one to take out the whole brain and look at it under the microscope. They discovered the blood flow to the brain. How is it that the things are connected? You may know that the connections in the brain of the main blood vessels is called the circle of Willis because of Thomas Willis. They established and developed the term reflex and neurology. Obviously, I'm really proud of them. But they also established the brain as the seat of the soul. Up to that time, mistakenly, people were thinking of the heart because the heart was kind of in the center of the brain and it was a tough organ and it was the one pumping blood. That's the main structure in the body. And they were the ones that realized our thought, our process, what we do, who we are, our connection with God, it comes from the brain. So at that time, we learned a lot in the 1600s about anatomy of the brain, different parts of the brain, how do they look, what names they have. They put names on structures in the brain. But it was not until the 1600s that we started to have 1800, 200 years later, that we started to look at diseases and how diseases that affect the brain correlate with different damages and different areas of the brain. And that job belonged to a guy named Jean-Marie Charcot. So Charcot was a French physician who finished medical school in Paris, and when he was in his early 20s, he was assigned to this Salpêtrière hospital, which was the disabled hospital in Paris. It was a huge disabled hospital in which patients that couldn't walk, couldn't talk, couldn't think, have mental retardation, seizures, epilepsy, whatever condition they had that they were disabled, they were thrown into the hospital without any type of neurological, physical examination history taken. So those patients were there. They knew they were disabled. Nobody knew what they have. So when he came there, he started a systematic evaluation of those patients. He would look at every patient, get some story about their development, examine them, figure out. He was the first one that figured out the difference of, for example, the essential tremor compared to the tremor from a cerebellar deficit compared from a tremor with Parkinson's disease. He was the first one that realized the difference between spasticity from a stroke and spasticity from Parkinson's disease. He was the one that described Lou Gehrig disease and multiple sclerosis, aneurysms in the brain. He was so famous that all over Europe, he had clinics on Tuesdays and Fridays where people all over Europe will come to his clinics in Paris to listen to his conference on neurological diseases. He published several books, and in the great times of France, where people would sit down in the evenings to listen to a neurological lecture, he was the one giving them back there. His lectures were social activity. So initially, in the front of the room, they'll have the neurologists and scientists and physicians of the time. And the back of the room, people from society would come to listen to his lectures. So he was considered the father of neurology, and most of what we know about neurology, basic disease knowledge, we owe to him. He performed a number of neuropathological presentations, meaning patients would die. He would look at the brain, look at it under the microscope, and then had a discussion with his students about the disease and what caused the disease based on what he would find on the brain. But at that time, looking at the brain was like looking at a piece of pudding or yellow or Play-Doh. There was no structures that you can look at. There was nothing looked different than anything else when you look at the brain. And that was the case until the late 1800s, where an Italian by the name of Gaudier developed this stain with silver stain, and they realized that when they put silver stain on the brain, the neurons will lighten up. So Santiago Cajal was a Spanish man, and he wanted to be an artist, and his father pushed him through medical school. He became a neuropathologist, and using the Golgi stain, he was the first one ever that was able to look at a brain tissue and look at it into the microscope. He made drawings of the brain, and this is the first picture that we ever had of this basic structure of the brain. The neurons, showing the neurons. These are Purkinje cells from the back of the brain, and showing how each neuron has so many connections and how they connect with each other. he eventually won the Nobel Prize not only for drawing and describing the basic structure of the brain, but he also postulated that cells didn't touch each other. So there have to be some kind of system in which how cells communicate with each other. So he postulated the fact that neurotransmitters, there was something called neurotransmitters, which are substance that a cell produces that is sent to another cell, stimulating some kind of function or some kind of response. I don't know about you, but when I learned neurons initially, my thought of a nerve cell was a nerve cell coming and having electricity and passing the electrical signal to another cell. Well, and that still holds true in part, but I think it's important to remember that when you look at the cell body of a neuron, this is the axon or the tail, each of those neurons at any particular time is connected with 2 to 10,000 other nerve cells. So the complexity of the connections on the brain is very detailed. So the neurotransmitters is a concept that, thanks to the previous scientist, Santiago Ramon Cajal, it was developed in the early 1900s. Acetylcholine was the first one discovered in 1921. I don't know if you know what acetylcholine is or what it does, but it does a lot of function depending on the part of the body. It's responsible for muscle contraction, but it's very important in the brain. And actually, if any of your loved ones or yourself is having memory problems and somebody has prescribed Exelon or Aricept, those medicines, they increase acetylcholine in the brain. So there's about 100 different neurotransmitters. They have different receptors. So not only we have like 100 different neurotransmitters, but every neurotransmitter may have 3, 4, 5, 7 different receptors, and every receptor have a different function. So our knowledge of how things happen in the brain and how different parts of the brain do different functions was a slow and painful process of detailed scientific observation through the years. The first time ever that we were able to recognize that a part of the brain performed certain function was from the studies of the young scientist Paul Broca. He was a physician, a French physician, who followed this patient who previously had a perfectly normal speech. And as time went by, his speech started becoming a little bit more hesitant, more fragmented, and he basically lost his ability to pronounce. So he lost his ability to produce. He could think what he wanted to say, but he couldn't make the words. All he could say was tan tan. So you ask him about his name, what he was doing, tan tan, tan tan. That's all he could say. So they'll call him in the nursing home, El Señor Tan Tan. So when he died, Broca looked at his brain, and I don't know how this shows, but you can see here the temporal lobe. That's the frontal lobe, which is the bigger of our brain lobes. And on the posterior and inferior part of the frontal lobe, on the left side, there was a damage. This particular damage was caused by syphilis that has spread from you-know-where to the brain, causing that lesion, leaving him with that deficit. So following that, there was a number of studies that started giving us information about the different parts of the brain and what did they do. And one of the more interesting was a story on a guy named Phineas Gage. And he was a railroad worker in England. And he was working one day on his railroad, and they hit an explosive, and this metal bar came up and hit him on his face, damaging his eyes, having a right frontal fracture, damaging most of the frontal part of the brain. So he almost died. He was sick for a long time. He had infections. But eventually he recovered fine. He could talk normally. His memory was fine. He remembered everything fine. He had no motor deficit. And while before the accident, he was a mild-mannered, highly competent worker, after the accident he became fitful, antisocial, irreverent, foul-mouthed. I mean, he would indulge in the grossest profanities. I mean, he became totally antisocial. He couldn't work. He couldn't handle a job. His friends, didn't want him. And the physician that cared for him for so many years, when he died, they look at the brain and they realize that most of the frontal lobes were totally damaged. And that was the first indication that we have of how the frontal lobes of the brain, which, by the way, are the part of the brain that it takes longer to develop in our adolescence, is a part that have to do with personality, behavior, and impulse control. Okay? And there were many, many studies on strokes, for example. Strokes, as you know, is death of brain tissue. When there's a stroke, there's damage to brain cells. And obviously, through the years, looking at different strokes, we realize what different parts of the brain, what function do they have. So through the years, through injuries and strokes and accidents and looking at the brain, we started having an idea of what different parts of the brain do. But at the same time, laboratory research started to build up, through the years. And there were many people that we can talk about, but I just want to mention this particular gentleman, Eric Kendall, who in 1983, with his team in Columbia University, they were the first one that realized how is it that memory is function? How is it that cells connect to each other to form memories? Now, before that, before his case and his studies, we have known that short-term memory, which is the ability to remember something for a few minutes, like if I give you a number, 8735439, you repeat it a few times, it's on the short-term memory. And that's established through some nerve circuits. But for long-term memory, the brain has to produce proteins, and it has to produce synapses. It has to produce connections between one cell or the other. And he was the one that was able to recognize that. For that, he and his colleagues and other people doing other work on the brain won the Nobel Prize in the year 2000, the beginning of the 21st century. So just a word about memory now that we're in the topic. Because we all think that our brains are better than they actually are. Sometimes we forget how long it took us for us to remember a face or remember a name. How many times we read the same things and forget about them. How many times you repeat the same things in school. So memory is not easy. It depends on a number of factors, including emotions. When you learn something that is attached to an emotion, if I tell you something that it really calls your attention, there's a good chance you're going to remember it more than if it really have no importance to you and you're just trying to memorize a fact. The other thing that people think is that memories are like drawers. That you have a memory of something that you did, and then you put that information in a file in the brain and put it on the drawer, and then you're going to think about it, and you pull the information and you think about it, and it doesn't work like that at all. Actually, our memories are changing every time we think about something that we do. And I think that a good example for that is my wife and I. So my wife and I take a trip, and our purse got stolen, our train got delayed, our friends don't show up to pick us up. I had a few days of diarrhea. She's sick for a few days, And when we come back, her memory is focused on all of those things, and I forget about those things, and I remember about the views and the good times and the meals and the things that we do. So the point here is. We do create our own memories. I mean, you influence your memories, and I think it's an important concept to understand that memories change with time, and you can make them better or worse depending on how you look at things and your attitude toward life. So, what are our windows to the brain? I mean, we have talked about injuries to the brain, opening the brain, looking at it under the microscope, but through the years, what techniques we have to look at the brain, understand the brain function, how have they helped us in the last few years, and how are they helping us, and what new technologies have been developed for us to understand better how the brain works, and what else can we learn about it. Back let's start with the electrical function of the brain. And I have to say that all of the topics I'm going to cover is going to be very simplified. Every single thing I talk to, there's far more to it. We just don't have enough time in this next, half an hour, 45 minutes we have. But back in 1924, in Germany, Hans Berger developed the electroencephalogram. It's a machine to monitor electrical activity of the brain from the scalp. Very crude machine, because To get electrical information in the brain, it has to go from the brain through the fluid, through the fat, through the skull, through the hair, and through the brain. So you miss a lot. Still very useful. We still do it. But this was the beginning of further electrical studies of the brain. We realized doing that if you're taking a patient, part of the skull out temporarily, and you put a grid of electrodes in the brain, you can monitor the patient brain activity very well. Doing that, you can actually do monitoring of the different parts of the brain and have a far better understanding of what do different parts of the brain do. What exactly, what gets activated when you're thinking of doing something, when you're moving a finger, when you're moving your hand, when you're making a signal, when you think of doing something versus when you do it. That activates different parts of the brain. So those things we were able to learn through electrical monitoring. Through electrical monitoring, for example, in treating our patients with epilepsy, we realize that many patients that have epilepsy, the epilepsy starts on the temporal lobes. So patients that have a temporal lobe epilepsy, you can go in and you can detect that the seizures are coming from the temporal lobe, screen that, do a surgery, and in many cases you can cure the epilepsy. It doesn't work, obviously, that well or the case. One of the interesting examples is the case of H.M. Henry. Was a patient who, back in the 1950s, where we were already doing some seizure monitoring and surgery for epilepsy, he was sent to a hospital, university hospital in Connecticut, because intractable epilepsy, intractable seizures. He was having frequent convulsions. So they did some seizure monitoring and realized that his seizures were coming from the temporal lobe. So they did a surgery on one temporal lobe, and he improved, and the surgery went fine, and he did well, but he was still having seizures. So they realized that there were seizures coming from the other temporal lobe. So they decided, well, let's go ahead and take the other temporal lobe out. So they eventually resected both temporal lobes, not realizing that in the temporal lobes, in the medial part of it, there's a structure called the hippocampus. And in the hippocampus, on the medial temporal lobe, all of the memory that we process, it goes through the air. So when he woke up from the second surgery, he was cured from his seizures, didn't have any more epilepsy, but from that point on, he could form no memories. So that was the last time when you asked him about presidents, he never knew Kennedy. He has been the most studied patient in the history of neuroscience, and thanks to him or his surgeon, depending on how you want to look at it, we were able to recognize that all of the memory get processed through the temporal lobe, or most of it. It was interesting because through years of studies, they realized that even though you would come to his office weekly, to his hospital or to his room weekly for evaluations, and he would claim that he would not recognize you as time went by, there was some familiarity to it. When you show him crossword puzzles, every time he did them, it was new for him, but as time went by, he was able to run by them quicker. So there's some memory that goes through emotions that doesn't go through the temporal lobe, but most of our cognition, our ability to remember that you were here, who's somebody that you learned, some data that you learned, everything goes through the temporal lobe. So the electrical importance of the brain, we know the whole brain connects through neurotransmitters and through electrical signals. So it's a big cable electrical system. And we've been able to recognize that if we can control, block, stimulate some nerve pathways, we can control behavior, personality, and disease. And that's the data between a procedure called the DBS, the deep brain stimulation. We have a nice presentation here in Ocala a few months ago about it, in which you put a pacemaker, just like a pacemaker here on the chest, and you connect the wires up to the brain, and you put cables in the brain blocking or stimulating some electrical signals. And through that technique, we've been able to treat fairly effectively many patients with Parkinson's disease, tremors, Tourette syndrome. There's some studies of Tourette that you can control, major depression, and obsessive compulsive disorder. So controlling electrical signals with technology that we have now has helped us, and this is something that is a technology that's growing. It's going to be able to help us controlling these patients better. There's many ways in which we're looking at ways in which we can control and use the electrical function of the brain to treat and heal diseases. The VNS is a vagus nerve stimulation. It's another pacemaker that you put on the chest and you connect to the vagus nerve, and in patients with epilepsy, you can control them. Just this year, we have a procedure, a device called the NeuroPace. And the NeuroPace is a procedure that you put inside the brain in patients that have epilepsy that is intractable, and it detects when the brain is throwing these epileptic discharges, so it shoots them back just like an on-demand defibrillator, doing exactly the same job. It shoots electrical signal to slow down those abnormal electrical signals in the brain. Just came out, and there's a lot of new technology that we're developing, and this is a huge growing field. And one of the biggest areas which my friends here from IHMC are working on is how can you get somebody that have a spinal cord injury, that have lost a limb, and you can connect the brain directly. You know exactly where the function that control the thumb and the grip and the finger movement is. You can put electrodes there and throw a cable system and control it to an artificial limb and do function. And that's technology that we're starting to see. I don't know if you've seen over the last year studies with spinal cord injury patients where you can bypass, connect some of the structures, and we've seen for the first time ever patients be able to walk again, take some steps, and perform some functions with extremities that were totally useless before. So this is a huge field. It's a growing field, and the future of neurology, in big part, it depends on how we're going to be able to manipulate the electrical system of the brain. But nothing of this would have been possible if it wasn't because of imaging techniques, okay? Radiological techniques. X-rays, plain X-rays developed in 1985. The world was shocked by the discovery. The first ever X-ray was done on the wife of William Röntgen. It was her hand, and she couldn't sleep for days. She thought it was something like diabolic when she was able to see her bones on a picture of her hand. Technology progressed. By 1972. We had the CAT scans available. I mean, think about it. In the 1960s, if you have a brain tumor, a bleeding on the brain, we have no way to diagnose those. Eventually, the technology that led to the discovery or development of CT scan led to a Nobel Prize in 1979, and within 10 years later, in 1982, we had the first MRI. And MRI, I tell you, I mean, I went through medical school, never seen an MRI, came to my training in Birmingham. They had a new MRI machine, and I remember those first pictures, and I'm still amazed by them. I mean, the ability that we have to take a look at the brain and look at details and treat the patients. I mean, this particular patient, if we have seen back in 1970, with 3 months of progressive headaches, a little bit of imbalance in coordination, personality changes, we really have no way to work him up or treat him effectively. Now this patient is coming. We get a CAT scan. We realize that the patient have a right frontal lesion. By the appearance of it, we're strongly suspicious that this is a glioblastoma, a malignant brain tumor. And then depending on how the patient is doing, we can examine the patient. We can decide do we need to do surgery? Do we need to do radiation? Do we need to give some medicine to decrease that swelling? I mean, this is a patient that otherwise before this technology would be death in a few weeks. And now we have the option of treating and hopefully improve the quality of life for a period of time. They're still going to die later on, this particular patient, because this tumor grows like in roots. So even if you take what seems to be the core of the tumor, you're going to have tumor cells growing in. But obviously, this has improved significantly our ability to diagnose and treat neurological diseases. Branching from MRIs, there's a lot of new technologies that have enhanced tremendously our ability to understand the brain function. One of them is a functional MRI. Putting somebody on an MRI machine and telling them to think of something, do something, move something, and then record the part of the brain that gets active. So we've been able to do some more very fine brain mappings. If you look at the picture on the left, you can see, oh, here we are. We can see, for example, if you're learning a task, the parts of the brain here on the temporal lobe, a posterior frontal lobe that get activated. If you're recalling something, these are the parts of the brain that get activated. So this study, the functional MRI, it pinpoints regions of the brain that are activated, that are recruited, that are working during a mental task. And then you have the PET scans, another technology that we've been using clinically to help diagnose some patient with Parkinson's disease and dementia and frontotemporal dementia and other conditions. But it also has helped us tremendously in our study of the brain. Look, for example, at that picture on the left side, what parts of the brain get active when we're hearing words compared to when we're seeing words. What about when we're speaking or when we're thinking about words? So our ability to understand how the different parts of the brain work, what function they do, is being tremendously enhanced by all this technology. And this is something really fairly new, the diffusion spectrum imaging. This sounds like an artist had nothing else to do and he started painting this. Okay, this is a computer-generated picture of a diffusion spectrum image where you can get, an idea of how the nerves are wired. And they're wired like in electrical grids. You can take the 100,000 miles of nerve cells, enough to go around the Earth several times, and we're figuring it out. Exactly. What part of the brain connect with each other? How are those connections influence our ability to function, our ability to improve when somebody have damage? So this is one of the new technologies. And PET scans, for example. PET scans and functional MRIs. Oh, I'm that late already. Okay, I'll go quickly. So PET scans and functional MRIs have given us information, for example, of sex. What part of the brain get active when you're thinking of sex, performing sex, masturbating? They've done studies on all those. They've done some studies recently looking at bisexual patients. And they put them to smells of males, smells of females. And they notice that the brain get activated and excited with both males, showing potentially some scientific basis for bisexuality and homosexuality. And still, these fancy studies provide a lot of useful information, but sometimes some of the simple studies provide tremendous data. Like this particular study is a psychological study done at FSU. I don't know if any of your children or grandchildren go there, but keep this in mind. So they did a study in which they took about 50 students, and they have this good-looking woman approach them and tell them, hey, I've been watching you for a while. I really like you. You're a good-looking man. My apartment is off. Why don't you come and join me and approach them for sex? And the same thing happened with females. They brought these good-looking guys and told them kind of a similar story, charming story about how much they like them and appreciate them. I've been watching them and know about them and wanted to get intimate with them. So of those, 75% of the FSU males approached by a good-looking female agreed to have sex with her upon request, while none of the females agree. I think I look at this as a simple example of how males, we have the reptilian brain more active, while the women are still using the cognitive function a little bit better than we do. Well, we've been able to map down how is it that the brain function. I mean, what is it that controls sex and sex impulses, for example? I mean, we know that connections of neurochemicals and dosages of neurochemicals on the brain had a lot to do with your desire for a person, with your desire for intimacy, with how much you like somebody. Dopamine, for example, very active on the early stages. When you're obsessed about the girlfriend that you really like and you want to spend all your life with her and all the time with her. Serotonin, they call it the love molecule, one of the most important chemicals, keeping the subject of affection on your thought. Oxytocin, this is really interesting, the bonding hormone. Animals, mammals, that have high oxytocin level, okay? Monogamous animals, the prairie vole, the little rat-like thing, I don't know if it's a rat or whatever, they have high levels of oxytocin. They have one mate for life. When that mate dies, they never mate with anybody else. While animals and mammals that have low levels of oxytocin, they're very polygamous. And it's far more complex. There are many other neurotransmitters that have to do with brain function. And now, if you can imagine, if we're looking at what happened in the brain during sex, are people looking at the brain? What about God? What is God here in all this? Well, there's a lot of studies actually going on. And I tell you, the data on this is incredible. And I didn't have a chance to look into it because it would take me another 2 years to get this ready. But there's something called, here we go, sorry, neurotheology, okay, neurotheology. The goal of it is to determine what's happening in the brain during a religious experience. I mean, we know, for example, if you're thinking of God, if you're in connection with God, if you're praying, what part of the brain get activated, and people are making maps about that. This is a particular book. The God part of the brain, in which the author makes the argument of how we are hardwired to believe in God. So very interesting data coming out of our connection with God. We know the connection with God is in the brain. What exactly it is and how does it work, we'll have more information. You get somebody else to talk about that later on. We look at criminals. We look at intelligence. What makes the brain different? In criminals, for example, you remember that limbic system? Okay, that system in between, the emotional system. This criminal that have no concept that they've done anything wrong, they have very small anterior cingulate gyrus. The psychopath have have a less dense limbic system. So we can take a patient and look at them through PET scans and functional MRI and have an idea of how are they doing, what makes them behave the way they do. This technology of understanding the brain issue, the brain tissue, how it functions, the connection and the potential that it has is being so interesting that just last month, the NIH opened this plan in which they have this 12-year effort to map the brain connections and all the neurochemical process. The goal is to take all the genes, look at the genes that are active on the brain, look at the connections, see what connects with each other, look at the neurotransmitters, how the balance between the different neurotransmitters control the brain. This is a project that so far is being sponsored by the NIH, the National Institute of Health, the American Academy of Science, and also the Department of Defense is involved in this project. No surprise, actually. Let me briefly talk about the senses, okay? Because so far we've been talking about the brain and the brain tissue and the connections inside the brain. But what are the senses? How do we connect with the outside? And that's exactly what the senses do. So the brain takes all of our sensory experience and make them into memories and responses. That's exactly what the senses do. So when we look at the senses, touch, I mean, the skin is the biggest organ in the body. Stimulating the skin is so important for development. How those receptors in the body function, how do they work when they dysfunction? Why conditions like fibromyalgia, that as far as many people a few years ago or even now consider that a psychological and emotional problem, how we know exactly that these people have an increased susceptibility to pain. We've done that through functional MRIs and spinal fluid studies. We've been able to map the pain connections and look at exactly what part of the brains get active in somebody suffering pain. We've been able to study audition, the importance of hearing. You know, how when you get a baby exposed to a fluent speech and through different types of musical tones, it helps enhancing the brain connectivity as far as comprehension and speech is performed, and how can that help us to train our kids from early life to develop speech and a second language. What about taste and smell? Those are two different senses, but they work together. You know, they are really our defense of things that get into the body. The taste and smell is what tell us, you know, what is good and what is bad for us to have. You know, some people give them the same importance, but when you look at taste, we only have 5 different taste buds receptors. So they give us sweet, sour, salty, bitter, and something called umami, something like that. While the smell, we have about 10,000 different smells receptors that in combinations can detect about 100,000 different smells. You know, and it makes sense because if there's something that is really going to be bad for you to eat, you want to smell it before you put it on your mouth. The smell is something that in lower, I don't know if that's a good word, but in lower mammals, it's a more important sense. You know, many mammals depend on smell more than anything else. In humans, because of the development of vision, our smell kind of took a secondary place in our senses. However, smells are critical, particularly we choose our mates through smell. And there was a very interesting study done talking about this, in which this investigator took 40 males and give them white t-shirts, never been used before, and the guys slept without deodorant or perfume a few nights with the white t-shirts, and then they give the white t-shirts to 40 women. So the women have to smell the shirts, and they have to make a decision, they have to rate them. Well, you know, I really like this guy's smell. I'm attracted to this one. I want to have intimacy with this one. This one is disgusting. What they found on that study is that the women find more attractive, based on the smell, the males that have compatibility on their immune system. So smell is important to choose our mates and to choose a mate that will help us breed healthier children. The vision we know is the most important, and what happened with the vision is that in one of our ape ancestors, they develop color vision. So with color vision, humans were able to look outside at a tree and figured out that that one has some green apples, showing that they were ripened and ready to eat. So the development of vision kind of overwhelmed some of the other centers and became the more dominant sense of humans. I'm putting this slide because I thought it was interesting. There was a study looking at how females examine faces of people compared to males. Everybody starts kind of from the nose. And then from the nose, you know, we go to the eyes and go to the lips. But, I mean, it's been well known that women are able to recognize faces a little bit better, and you can see why. You know, they start looking at you, and they start looking at every single detail of your face. So there was a study showing the movement of the eyes of a female examining a face versus a male. So, trust me, there's a lot of difference between male and female brain function in many aspects. It's very interesting. It's very interesting how, we think that the things we look, that's the way our brain captured them. But the brain captures fragmented things and is able to put them together. And that's why, for example, some people that have some damage in certain parts of the brain may be able to recognize maybe you by the hat and you by the glasses and you by the shirt instead of recognizing you as a whole. There was an interesting study. This came out this year. You know, any study that have to do with Jennifer Aniston, I like it. But they did a study on Caltech and UCLA. Very interesting study in which they presented pictures, and they were able to do very detailed monitoring on these patients. And they realized that a single cell connection, a single synapse, was able to be activated when patients responding to pictures of Jennifer Aniston. So it seems like the recognition of a face, you know, can be boiled down to just one single nerve connection, which obviously follow-up studies suggest that relatively few neurons are involved in representing any given person, place, or concept, making the brain staggeringly efficient in storing information. The senses are interesting, but as anything in humans, nothing works exactly perfect all the time. And sometimes it happens that there's some people that have the capability or the problem that sensory stimulation can cause sensation that is normally experienced by others. For example, if you touch too hard, if the light is too strong, if the smell is too strong, if the sound is too strong, you're going to feel pain. So pain, which is something that you normally think about it as a tactile sensation, you can have it when you stimulate other senses. But the best example of how one sense can capture qualities of another sense, it's outlined on the work of this famous painter, Vasily Kandinsky. He was a father of modern painting. He was a Russian-German painter who developed abstract painting. And I don't know about you, I'm not a big abstract painting fan, but when you see his work, it looks like, when it tells you something is coming out. He was able to perceive music sounds as color. He actually named most of his paintings like with symphonies, and it's widely believed that Kandinsky have a condition called synesthesia, that you have it on your handout there. That's the ability to be able to perceive some sensory stimulation with the characteristics of the sensory system. For example, he would perceive music as colors. So a lot of things can go wrong in the brain. Sometimes the senses fail us and don't work quite right. And sometimes we perceive things that are not there. That's what an hallucination is. So hallucinations can be visual, like this, can be smell, can be tactile, can be auditory hallucinations. But it's basically an image or a sensory perception when the stimulation is not there. And obviously, when you think about the complexity of the brain and all those nerves connecting with each other, and every cell connecting with another 10,000 other cells, you realize that at some point something is going to go wrong, leading to things like mental illness, depression, anxiety, psychosis, bipolar disorder, which we don't have time to talk in more detail. But all of those are, many of them, genetic disorders. The more we look into genes, the more we realize that more conditions have some genetic influences. What about creativity and mental illness? And, think about Robin Williams. He's only one of many examples of how people that have tremendous creativity also suffer from often mental illness, particularly bipolar disorder, which Munch suffered from severe depression, Van Gogh suffered from vertigo and severe depression, possibly bipolar, and Frida Kahlo had some depression and chronic pain. So in order for the brain to function well, as complex as it is, it needs rest. It needs some rest. So that's why we sleep about 1/3 of our time. That's why we need our sleep. So I'm not going to go deeply into this because I'm running a little bit late already. But through the night, we go through 5 stages of sleep, and that's coming cycles. Stages 1, 2, 3, and 4 are the deep sleep. That's the time where the brain does for recovery and healing, the cleaning of all the process that went on through the day with all the function and all the thinking. And then the REM is the rapid eye movement. That's when we dream, and that's where we consolidate memories. Okay, so we go through these cycles through the night. The sleeping changes from life. And siesta, yes, is good. I'm sorry I'm taking your siesta time. But people often ask me, my husband never took a nap when he retired. Now he's retired. Now he's taking a nap every afternoon. And I tell them, well, let him take his nap. Let him sleep. Nap is good. It's important. This is a nice picture about what's called the nap attack. 7 o'clock in the morning, 8 o'clock, no much problem. Afternoon, start getting a little tired. But 4, 5 o'clock, 6 o'clock, that's where we are now. That's when we start feeling tired. And a perfect nap is a short nap, definitely less than an hour, 15 to 30 minutes, not in your bed, get your feet up, take a good nap. It's healthy, it's good for the brain. So there's a lot about the brain. This slide tells me that we have only 5 more minutes to go and cover a few brief things. I know I'm taking a lot of your time and your mental effort. And I just want to mention 2 things of this slide. Okay, there's far more we can talk about. We could make a whole conference of this picture. But there's a couple of things that I want to point out to you here. One of them is this structure here in the middle called the corpus callosum. The corpus callosum is the part of the brain that connects the right side with left side of the brain. It's one of the main differences between male and females. Females have it bigger, so they can do more multitasking than we can. The other important part of the brain that I want to mention is this little structure here, okay, called the pituitary gland, better known as the master hormone. That's what controls the rest of the hormones in our body. So the brain not only controls everything we do and think and how we move and how we behave and our responses, but it controls the rest of our body in all ways. So what goes wrong? I mean, if you live long enough without a stroke, without a trauma to the brain, without developing mental illness, what causes brain damage. Well, we have known for a long time that one of the more common causes of Alzheimer's and a number of other neurodegenerative disorder is outlined on this picture. Normally, in the body, the proteins have like a helix form, okay? A helical form, a helix. That's the way proteins are formed. And as we get old, for many reasons, some genetic disease, some aging, some other factors, that helix starts to become weak and unfold, affecting the function. And this is one of the more common causes of Alzheimer's disease. It's one of the bases of Alzheimer's disease. Not the only thing, because strokes and circulation problems contribute to Alzheimer's as well. But the unfolding of protein on the brain, it's become to know one of the most important things in why, as we get old, the brain starts to fail. And we have now drugs and studies that are looking into the possibility of keeping those proteins from being unfolded. Very interesting data coming out. So as we get old, physiology, the brain, have all the neurons that we have. They start connecting with each other. The brains become mature when we get to be 22 to 25 years of age. And then the brain starts to get old in a slow process. So seemingly everything gets worse as we get older, except with this green line. Okay? If you follow that, is the line of the emotions. As time goes by, we improve in our impulse control, decision making, and judgment. Our judgment, or what is thought as wisdom, tend to improve as time goes by. So we need to focus on the things that we maintain and can still make us better than the youngest one and make it improve. This is a list of 15 suggestions that I give my patients in the office about things to do to help the memory. Work on your schedules, stay active, keep a low carbohydrate diet, have your 3 meals a day, plenty of fruit and vegetables, including berries. Exercise on a regular basis, get a little bit of sun, staying indoors is not healthy. Cut down smoking if you're still doing it. Stay physically active. Schedule your house chores. Hydration, get involved in social and family activity. Contact your old friends and for friends with known warriors. Laughing is healthy for you. Plan something enjoyable every day. Learn new skills. Play cards, play board games, listen to music. Consider going to the church or religious service of your choice. Take your breaks for the trip. Take your breaks for fun. Eat healthy. Have a glass of wine every once in a while. One of my heroes, Rita Montalcini, she was a 20-something-year-old physician working in Italy under Hitler and Mussolini. Back in the 1930s, he was performing some studies on neuroscience. And everybody, all of her friends were telling her, you need to get the hell out of this country right now. I mean, you're a young Jewish Italian working here. Get the hell out of here. And she would say, I'm not going to leave my work. She continued to do her neuroscience research. He was one of the first persons that described apoptosis. Is the tendency of cells to die on their own when the time comes. He discovered the nerve growth factors and ended up learning the Nobel Prize because of that. She worked until she was 100 years old. She claimed that the secret of a healthy brain lays on maintaining physical activity, curiosity, and passion. And the last 3 slides that I have today is just 3-4 slides just talking about some of the new things coming on the brain. Where are we going with the brain research? We talk a little bit about the changes on understanding the electrical function of the brain, but one of the biggest things that scientists have been working on in the last few years in terms of biology of the brain is something called plasticity. It's a single topic that has dominated brain research in the late 90s and early 2000s. It defines the ability of the brain to reshape and reorganize itself through adulthood. Most of us I grew up thinking as a neurologist that once the brain is solid, it's not going to change. We know there's strong evidence that that's not the case. You can teach the brain some new skills almost at any time in your life, and that's critical to remember. What about stem cells? I mean, stem cells sounds like a magic word in terms of brain research. It's been discovered a long time ago that if you take rats and you put them on a very active environment where they're very stimulated, they're going to be able to produce new cells on the hippocampus. Okay, remember? Medial temporal lobe, where all the memory is processing. We know we can do that in humans as well. It was discovered back in 1996 that we have stem cells actually in our brain, and we have some maps of the brain where we know where our stem cells are. How can we stimulate them to form new cells and new connection and evolve into cells that are useful for people that are losing them? Obviously, it's been a huge task for science. And I just want to end briefly talking about infections and humans, a topic that people have not been paying a lot of attention to. We have in our bodies 10 times microbes than human cells. So we have more microorganisms and viruses in our body than we ever imagined. So if you look at the genes that we have, a human have about 20 to 25,000 genes. But when you look at the genes on the microbes that we have in our body, they're about 3.3 billion. So those genes of the bacteria that you have in your intestine, in your nerves, in your body, their influence, your susceptibility to illness, infections, your mood, your behavior, your multiple sclerosis, you name it. So I had the opportunity to interview Carl Zimmer, who's considered to be the best science writer of the last 20 years, about different things, and I asked him this question. You have written extensively on a wide variety of medical topics. Any important discoveries that have been overlooked by mainstream medicine? And he answered, we are home to 100 trillion bacteria and other microbes that produce or synthesize vitamins, influence our weight, protect from disease, make us susceptible to others. The doctors need to envision the human body as a superorganism composed of thousands of species, not just one. And I'm late. I know you're tired. You probably have a sensory overload. But I'm going to hold there, and I'll be glad to take any questions or comments from you.